Hi 253. In this video I'd like to discuss an interesting example from section 10.1 where we were discussing parametric curves. We already discussed the cycloid in class together, observed its equations, its parametric equations, as well as what its graph looks like. Remember that the cycloid is generated by a rolling wheel, and what I'd like to do now is actually consider another rolling wheel example. So here's the definition of what's called an asteroid. The path of a point on a circle A, we'll call it circle A, with radius little a over 4, right? So that's the radius of circle big A. So the path of a point on this circle that rolls on the inside of a circle big B with radius A is called an asteroid or hypocycloid. Its parametric equations are given by the following. So we have x equals a cosine cubed t, y equals a sine cubed t for t being on this interval 0 to 2 pi. Now this kind of sounds a little bit confusing in terms of what the action is that's actually generating the path of the point, right? You're talking about two circles, one is rolling on the inside of another, and we've got this relationship between the radii here. So let's see if we can actually generate a picture of this asteroid with a certain value of a. Remember, we've actually observed this value of a here before when we constructed the parametric equations for a circle, right? We noticed that this a here had an effect on the radius of the circle that we were considering. So we're probably guessing that that A there also has the same kind of an effect in this problem. So let's graph it, and then we'll see if we can come up with the equation in terms of x and y. So remember, I provided you with a link to a parametric grapher on your Moodle site, but I have also gotten an animation here from your textbook resources. This is through the Wolfram CDF player, so we have an interactive feature with our textbook. And this right here actually is representing, we'll see in a second, the path or the graph of this parametric curve here from these parametric equations. So notice we have x equals a cosine cubed t, y equals a sine cubed t, just as we had in our slide, for t being between 0 and 2 pi. Notice that we're expecting, hopefully, that the entire path will be generated on this interval of t because we know that the period of sine and cosine is 2 pi. So we're expecting a complete path to be drawn out here on this interval for t. So let's take a look at what we have in our picture here. It looks like we have a big circle, big B here, right? And then we have a little circle. It's not labeled, but this is little circle A, right? Yes, and notice that the radius of this here is 1/4 the radius of big circle B, right? And we've got the radii of big B being labeled as small a, and so the radius of circle little a is 1/4 a. So let's take a look at what the path looks like as we allow t to go between 0 and 2 pi. So let's take our little cursor here and wind it back, and it kind of spoils the surprise, doesn't it? Yes, when I wind it back like that. But let's hit place here so we can see what happens as t moves through that interval of 0 to 2 pi. And we notice that the point on the circle big A is a fixed point on the circle, and that circle big A is rolling on the inside of circle big B here. So let's see what happens if we actually modify the value of A here, because notice we have A equals 1. That's the circle we're actually working with right now, and this little slider here allows us to change the value of A. So A is the radius of circle big B, remember. So if I make it smaller here, yes, say to 0.6. Let's rewind our player here for a second. Let's see what happens now. So it appears that just by modifying this value of A, we are modifying the size of our asteroid, yes? And again, it's all because we're rolling on the inside of this circle of radius, little a here. And we can actually make it larger than 1 also. Of course, we'll just get a really nice big asteroid when we do that. And let's reset that and hit play. And notice that the center of that circle, big A, of course, consistently moves in a circle also. Yes, because it's a fixed point here in the center of the circle. So that's exactly what an asteroid looks like. The asteroid is actually the black path you see here. Yes, that was the point drawn out by the circle on, the point on the circle big A right there. Now let's take a look at how we can actually come up with the equation in terms of x and y. So we noticed that cosine and sine have a period of 2 pi, so we did get, in fact, a complete curve. Let's see if we can eliminate the parameter t. So note the following. If we are clever here with the power on x and y, x to the 2/3 and y to the 2/3, we actually get a nice simplification of the sines and cosines here by using the Pythagorean identity. So we arrive at what's called an implicit equation for the asteroid, x to the 2/3 plus y to the 2/3 equals 1. Yes, and our other animation here from our Wolfram player here allows us to see how this asteroid is actually generated without the use of the circles here, but more relying directly upon the parametric equations that we have. So these smaller graphs here are showing you how the ordered pairs are being produced, how the value of x is being produced as t varies between 0 and 2 pi, and how the value of y is being produced as t varies between 0 and 2 pi. So let's reset our player here. And we see that as t progresses through the interval, we're noticing that the ordered pairs being produced are exactly the point that that red dot is on here. So notice that x was at 0 and y was at -1 when we were here at this lower point on the asteroid.